Welcome again to electrostatic field. Today we have a practice problem on Gauss's law for electricity. The title of the problem is electric field due to a uniform and infinite cylindrical of a uniform charge density.
The second example here is the same but for cylinder. We are told to calculate the electric field in finite cylinder, and it has again a uniform charge density rho v and center around z axis in the free space with just am. This we can draw this one. We have here z axis, and we have our cylinder infinitely lying center around this z axis with radius a, and we want to again to calculate the electric field in this example. So the solution is again, since this is symmetric around the axis, and use the cylindrical coordinate system. And again, due to the symmetry, we can conclude that our E is a function of rho and in the direction of rho. So again, just mathematical manipulation, we can find that D is also D rho as a function of rho. And this happened because this one assumed to be a constant. And so we can do separate the problem into two. One is inside the cylinder and one is outside the cylinder. First, we do the integration over the surface, which is inside the cylinder. This is our cylinder here. This extends infinitely along the z-axis. It has a radius a and charge rho v. And we have the surface. Our surface, we take Gauss surface here from minus L over 2. This minus is positive, and it has just a radius of r. We assume our assumption is that r is less than a. The left hand side first, n is equal to rho, as we concluded in the previous slide. And then we do the double integral dd and ds, which is after substitution you will get here rho, this replacement of n, and this is the vector which we concluded last slide. This is just infinitesimal element. Just substitute, move out the non-dependent components outside here, do your integration from 0 to 2 pi in for phi, and from minus L over 2 to L in case of Z. This one will equal to L, and this one will equal to 2 pi. So in total, they will equal to 2 pi L. Substitute in the original equation, and you get d dot n ds will equal to 2 pi rho L dr. Now we move to the right hand side. We want to calculate the enclosed charge. So we use this right hand equation. Rho v again is just constant. So you just do the integration here, which is rho v integration rho d rho integration d phi integration dz. The integration start from from minus L over 2 to L over 2, from 0 to 2 pi, and this one is from 0 to r, the enclosed charge. So doing this one will get r, this one 2 pi, and this one again is just L. This is rho square over 2, and in total you will get pi rho square L. And after you include rho v, then you have pi rho square L rho v. Then use these two results here and there and equate them together and simplify. Then you get d rho equal to rho v over 2 multiplied by rho. And then if you solve for e, you get rho v over 2 epsilon naught rho, and then you just multiply by rho to get the full vector. We move to the second case outside the cylinder, where your rho is more than a. This is your surface, the charge. This is z, this is a. You have rho b, and you are taking Gauss surface as a cylinder. Radius rho has height from minus L over 2 to L over 2. So left hand side will be the same, no change. as we have done before. And for right hand side of Gauss's law, you need to calculate the charge. This is constant, so we get outside, substitute was by d volume. This will reduce to 0 up to a this time, 0, 0 to 2 pi of our d phi, and 0 to not 0 minus L over 2 to L over 2 dz. The first, this one will equal to L at the end. This one will get 2 pi, and this one you get a squared over 2. Substituting this one, you get the integration here equal to 4 by a squared L, and substitute with this value here, you get by a squared L rho v. Then we do the equation here. We equate the two results, this result and this result. Then we got d by mathematical manipulation. Finally, we get the value of p rho as a function of rho, which is rho v squared over epsilon naught rho dot a rho. Just for your memory, we have calculated E for an infinite. Yeah, if we have very narrow cylinder here, or we call the wire at that time, and it has charge rho naught, and we are calculating the field somewhere, rho, phi, and z. We got the result that epsilon is equal to rho naught rho over 2 by rho epsilon naught. This is the result which we got from this problem, and actually this is also comparable to this one. This one, we when we applied Coulomb's law, actually. Anyway, you can manipulate here, and you'll find again this is just charge density over 2 by rho. Thank you.